Thanks for connecting to this session of Sapienza Neuroscience Seminars. This is the World Alzheimer's Day 2024, and the title of the presentation is Alpha and Alzheimer's Disease, Hans Berger's Dream Come True. I will be the speaker today. The history of World Alzheimer's Day begins on September 21, 1994 in Edinburgh, and was founded by Alzheimer's Disease International to promote the Alzheimer's Month in every September's and help global Alzheimer's associations worldwide. The Alzheimer's Day was founded to investigate the problems of Alzheimer's disease patients and the families worldwide. Every year there is a theme, and the theme for 2024 is time to act on dementia, time to act on Alzheimer's. And the scope of World Alzheimer's Days is typically to eradicate the stigma and discrimination of patients with Alzheimer's disease and family and advocates and so on, and to coordinate in a day a lot of initiatives of disseminations and discussions and meeting of people to understand better the Alzheimer's disease and the problems of Alzheimer's disease. And there is a special focus to increase the awareness of regulators, political persons involved in public health and aging and dementia. The title of the presentation is on the screen, and you see my co-workers at the Sapienza University of Rome in Italy. You can also follow our initiatives in the field of clinical neurophysiology, registering in the special interest group of International Federation of Clinical Neurophysiology, titled Advanced EG and MEG Techniques in Clinical Neurophysiology, in the website of International Federation of Clinical Neurophysiology. I have no conflict of interest in this talk. EG alpha rhythms were discovered by a German psychiatrist, Hans Berger, in 1924. The first recording was performed on July 6, 1924, in Jena, a German city. The first patient was a 70-year-old boy, and the recording was performed during the neurosurgery. And Hans Berger could profit a school defect, a school breach, to insert the electrodes and record the weak EG signal from the brain of the patient. Hans Berger was the first to term human EG alpha and beta waves from EG recording. I was the first to relate the scalp recorded EEG activity to the mental states of the participant. You see in the slide a photo of Hans Berger and the first equipment he used in his university in Jena. You see that he used a very simple single channel bipolar electrode montage to record and amplify EEG activity. And you see a picture taken from his experiment during the resting state, eyes closed condition in quiet wakefulness in green frame. And you see that the time scale of 1 second unveils an ample oscillation at about 10 Hz. He called alpha rims this primary wave in the EEG activity from the frontal occipital bipolar electrode. When Hans Berger asked to close the eye, open the eyes, you see that the ample alpha rim disappeared, and was evident a low voltage, high frequency EEG activity at about 20 Hz, and he called beta wave this rhythm. At the end of the recording in green, you see that he asked again to close the eyes to the participant, and alpha rims appeared again. He published the results of resting state EEG activity from the scalp, skull, and dura mater in several subjects in 1929, and this is the cover page publication. Nobel Prize for Medicine, Edgar Adrian, replicated the Hans Berger's experiment on EEG alpha rims, and you see that he used the same single channel bipolar electrode montage and the same conditions of resting state, eyes closed and then eyes open. And you see the results of these experiments. And again, you can see an ample oscillation of EEG activity at about 10 Hz during eyes closed condition at the beginning of the signal. And then the reduction or disappearance of alpha rims during eyes open condition. And again, alpha rims appear during the eyes closed condition. Adrian introduced also other conditions, for example, visual spatial task, and could show that alpha rims disappeared even in this case. The publication of Adrian's results was performed in 1934, 5 years after the Hans Berger publication. And here you have another important scientist at the time, Herbert Jasper, that performed the first EEG recording in humans in the United States of America. And you see the results. He replicated the setup of Hans Berger with a single channel bipolar electrode, frontal and occipital, And in the upper part of the picture, you see that there is an ample alpha oscillations in the eyes closed condition. And he introduced visual stimulation with the flashes, and the flashes induce the reduction of alpha rhythms you see in between the red arrows. And it's nice that when the light were switched off, no flashes, there was block of alpha rings, no alpha rings, for about 1 second. And this was related to the iconic memory of visual flashes. And so was a demonstration that alpha rings can be desynchronized not only for visual stimulations, but also for mental images of the stimulation. So another demonstration of the relation between EEG activity and the mental states of the participant. And the Hans Berger and Herbert Jasper published this confirmation of Hans Berger findings in 1935. This was another finding by Hans Berger. He recorded the EEG in patients with epilepsy, clinical diagnosis of epilepsy. And this is a case. You see that he recorded in 3 different periods. In the left side of the figure, you see that the recording was performed from one single bipolar channel before a seizure in this epilepsy patient. And you see that he could demonstrate relatively regular alpha rhythm. And he reported that the patient had a regular, quite vigilant state. Then he was able to record the EEG during the seizure in this patient, but he didn't publish the graphs, the results, due to the muscle artifacts during the EEG recording related to the seizure. But immediately after the seizure, there were no muscle artifacts in the recording, and it could show that the alpha rims was disappeared and was replaced by EEG activity at slower frequencies. And you show here this kind of sharp, slow wave in the recording. Hans Berger explained that during this recording, immediately after the seizure, the patient showed vigilance loss, another association between mental state and vigilance and EEG activity. In the right side of the picture, you see in the same subject the EEG recordings some seconds later, when the subject show a partial recovery of consciousness level and vigilance. And you see that there was some appearance of alpha rims together with slower frequency EEG activity. And Hans Berger reported a poor vigilance in this patient at this time of the recording. So what was the Hans Berger dream about the use of EEG in patients with psychiatric and neurological diseases? He dreamed that EEG could be useful to better understand the neural basis of psychiatric and neurological disorders. And also he mentioned the possible use of EEG activity to better understand the process of senile dementia in older people. And this second part of the presentation will be focused on the some findings from my group and other groups on Alzheimer's disease patients and related disorders using EEG techniques. Dementia is characterized by severe cognitive deficits and disabilities in the activity of daily living, as worrying or shopping or preparing a meal and so on. And the patient needs a caregiver to support in these activities. And here you see two very diffuse diseases belonging to dementia in older people. In the left, Alzheimer's disease, characterized by two abnormal proteins accumulated in the brain. You see in blue A-beta amyloid, and in brown tau protein. And you see that there is an overlapping in some brain regions of amyloidosis and tauopathy. And this is a trigger of a neurodegenerative cascade and brain atrophy and a severe loss of cognitive functions. In the right side, you see other diffuse diseases belonging to dementia, Parkinson's and Lewy body diseases. And you see that they are characterized by an accumulation within neurons of Lewy bodies. And you see that you can have this kind of accumulation in neural populations of brainsteins, and then in the more advanced stages of the disease in the brain. The typical clinical assessment of patients with Lewy body, Parkinson, or Alzheimer's disease is focused on cognitive functions. And you see that the neuropsychological test evaluates the decline in thinking abilities, or memory loss, or planning and problem solving, visual spatial skills, language, and so on. It's important to know the Alzheimer's disease in the typical clinical manifestation is characterized by significant memory loss and decline in thinking abilities. These symptoms can be present also in Lewy body dementia or Parkinson's disease in some cases. But the important aspect for this presentation is that the clinical assessment doesn't use biomarkers to unveil vigilance dysfunctions in these patients belonging to mental fog or drowsiness or sleepiness. And the presentation will show that this would be possible with the use of the advanced EEG techniques. In fact, is easy from Hans Berger experiments to record scalp EEG in non-invasive and cost-effective way. And you see that in this picture that EEG activity is recorded by the is generated by neural systems located in the brainstem, basal forebrain, depicted in gray in this brain model, and thalamocortical circuits represented by black arrows in the picture. These ascending subcortical neuromodulatory systems regulate the cortical general arousal, and in relation to modulation of arousal in quiet wakefulness, there is the changes of EG alpha rhythms and other frequency bands rhythms. And you see in this picture that the clinical symptom related to these changes of EEG is a sort of mental fog, making less clear what is happening around us. The ability to maintain the vigilance can be easily explored with the resting state, eyes closed and eyes open conditions, like the paradigm introduced by Hans Berger one century ago. And this is a nice paradigm to investigate the EEG activity during transitions of vigilance from quiet vigilance to drowsiness or light sleep, for example, during the recording. From the Hans Berger first recordings, the research in the field was focused to localize the generators of scalp recorded EEG alpha rhythms. And you see in this picture that there is consensus that the main generators are the cortical pyramidal neurons, due to the spatial arrangement of the main dendrites, allowing the summation of postsynaptic potentials during brain activity. And this summation is related to ionic currents and changes in the scalp electric field captured by scalp electrodes. A nice demonstration of the sources of ongoing EEG in the cerebral cortex is due to Lopes da Silva, Fernando Lopes da Silva. He performed recordings from visual cortex of dogs with the stick electrodes penetrating in the cerebral cortex, and you see the representation of the contacts in black. And from each contact, he was able to record EEG during quiet wakefulness. And you see that based on time scale, there are ample oscillations at alpha frequency in the EEG in the visual cortex of dogs. And if you see the surface contact electrodes, you see, for example, in the vertical dotted line, upper peak of voltage opposite in polarity with the lower, deeper electrode contact. And this reversal of the polarity allows to conclude that the source generator of this activity is about halfway in the cerebral cortex. You see in this picture the red light due to the fact that the general interpretation is that an ample alpha rhythm in the resting state, eyes closed, is related to cortical inhibition in the neural population, and so is a sort of control neurophysiological mechanism controlling the excitation in the cerebral cortex. There were advancements in the techniques for analyzing the EEG, and so you see here sketch elementary oscillations embedded in the EEG activity. For example, 3 oscillations on different frequencies in the delta band, alpha band, and beta band. And you see that the changes in time of the voltage is the typical oscillation in the EEG activity, can be used as an input for fast Fourier transform procedure, FFT, to obtain the so-called estimation of power density, which means the square of the amplitude of the elementary oscillation of EEG activity. And you see that you have in the power density spectrum peaks in relation to the amplitude of EEG activity in the time domain. And another technique is used when you want to investigate the correlation, the interdependence of EEG oscillations between 2 recording channels. For example, one frontal channel and another channel in the parietal regions. If you want to investigate the interdependence of the 2 EEG signals, which can be related to some functional connectivity of the underlying sources, you can use spectral coherence or other techniques, and you can represent the results in the frequency domain. For example, the spectral coherences spectra. And you see that again, you have a peak in the relation to the frequency analyzed, and in this case is related to the interdependence of the EEG signals from 2 electrodes. With these techniques, Fernando Lopez da Silva was able to investigate the functional connectivity between places in the visual cortex of dogs. And you see here 2 electrodes in the visual cortex. You see the red arrows, visual cortex electrode 10 in the upper part, visual electrode 9 in the lower. And you see that he could record an ample alpha rhythm. You see the time scale in the bottom of the figure. And he was able also to record from lateral geniculate nucleus of the visual sensory thalamus. And you see again alpha rhythms from the thalamus. In the right side, you see the power density spectra from visual cortex electrode 9 with a power peak at 10 Hertz, alpha rims. The same is true for visual cortex electrode 9 with a big alpha power peak, but also in the thalamus, in the lateral geniculate nucleus, the visual sensory thalamic nucleus. And you see that exactly at the same frequency, showing that there is a network underlying the scalp, e.g. alpha rims. And this network is related to the connectivity between cortical areas and the thalamus. And this demonstration comes from the coherence power spectra. You see again that the coherence between the EG in the visual cortex electrode 10 and visual cortex electrode 9 show a dominant peak at 10 Hertz. And the same is true when you see the coherence spectrum for the visual cortex electrode 10 and thalamic lateral geniculate nucleus. Again, the dominant peak is at 10 Hertz. So the first demonstration that a cortico-cortical, a cortical thalamic network functional connectivity is related to scalp recorded EEG. Another demonstration comes from Fernando Lopez da Silva using simultaneous recording of resting state EEG activity and the resting state functional magnetic resonance imaging. And you see in the figure in red the bold signal from functional magnetic resonance imaging. And bold means cortical activation. And he could demonstrate that when you have a peak of bold activity in the cerebral cortex, you have a low amplitude alpha rims. So the activation of the cerebral cortex is related to reduction of alpha rim. In contrast, when you have a peak of activity in the thalamus, you have an ample alpha rims at the cortical level. So this means that the bold signal in the thalamus, so activity in the thalamus is able to induce the generation of ample alpha rims related to low cortical activity. So this is another demonstration in humans that EG alpha rims in alpha frequency is strictly related to cortical activation based on signals coming from the thalamus. So the research addressed the possibility to localize in the cerebral cortex the sources of scalp recorded resting state EEG activity. But there is a problem for this exercise indicated in the right side of the figure. You see that the electrode B records an EEG wave which is generated far from electrode B. Specifically, it is generated by the sulcus of the cerebral cortex AT. And the cortical region activated can be modeled by a tangential dipole far from electrode B. This is why these effects of propagation of the neural currents across the cerebral cortex, the skull, and the scalp to the electrode needs a mathematical model. in order to take into account these head volume conduction effects. And so there are several tools using mathematical modeling of head as a volume conductor, and mathematical models for the sources of the scalp recorded EEG, typically dipoles, equivalent current dipoles, localized over the model of cerebral cortex. And you see here Illoreta freeware, and we use this specific platform to give artifact-free resting state EEG activity to the model, and is for the estimation of cortical sources of EEG. And then we averaged the solutions in large cortical regions of interest: frontal, central, parietal, temporal, occipital, and limbic. We averaged the solutions, and we produce the power spectra of this cortical source activation at the level of large regions of interest, similar to big electrodes placed in large regions of cerebral cortex. And so you see the results of an experiment in which my group showed the strict relation of alpha source activity in the resting state, eyes closed, and vigilance consciousness level. You see the results are, were obtained in healthy adults. They receive the EEG recording before 1 night of sleep deprivation, blue traces in the figure, and after 1 night of sleep deprivation in red. And the recording was in the resting state, eyes closed. The same condition in the two recordings. But you see that after 1 night of sleep deprivation, red traces, the source activation in alpha, in parietal, occipital, temporal, and limbic regions of interest in the Illoreta cortical model show lower alpha source activity. So when you have 1 night of sleep deprivation during your resting state, you have some mental fog, mental fatigue, and the alpha rhythms is reduced. Another demonstration of the relations between alpha rhythms and the consciousness vigilance level was obtained in patients with post-COVID-19. After 1 year from the hospitalization for severe respiratory distress, we recorded EEG. At the time of EEG recording, the subject was recovered, but he claimed some brain fog symptoms, mental fatigue, difficulties in concentrating. And even without any objective cognitive deficit from neuropsychological test, we were able to show with a clinical scale from 3 to even 10 brain fog symptoms. And so we stratified the long COVID, post-COVID-19 patients into groups. And in the patient with more brain fog symptoms in red, we could demonstrate a significant reduction of alpha source activity in the resting state, eyes closed, in parietal and occipital region. And you see that healthy subjects without any infection of post-COVID in blue, and patients with post-COVID, but less than 3 brain fog symptoms, show normal alpha source activity. So we perform some experiments in Alzheimer's disease patients with the Euro-Asian PD Waves Consortium. You see a lot of researchers and institutions represented in this slide. And one of the experiments were performed in patients with Alzheimer's disease and mild cognitive impairment in red, as stated by cerebrospinal fluid diagnostic biomarkers of Alzheimer's. And we compared the resting state EEG activity with patients with the same level of mild cognitive impairment, but not due to Alzheimer's disease in blue. So the clinical manifestations were similar in the two groups of mild cognitive impairment patients. But one group was due to the symptoms were due to Alzheimer's disease. The other group were due to other diseases of the brain. So in red, you have Alzheimer's disease mild cognitive impairment, showing less alpha source activity in the occipital, parietal, cortical regions of interest. In the resting state, eyes closed. And you see also an increase in delta source activity in temporal areas. So at the group level, we could show a relationship between alpha source activity in the resting state eyes closed and the Alzheimer's related neuropathology. In another experiment, we compared the resting state EEG source activity in Alzheimer's disease with dementia in red, Parkinson's disease with dementia in green, and Parkinson's disease due to Lewy bodies in violet. And you see that when compared to normal subjects in blue, there was a big drop in Alzheimer's disease dementia group in red, in alpha source activity in occipital, parietal, temporal, and limbic regions in the mathematical cortical model. But there were also a reduction of alpha source activity in green in Parkinson's disease dementia, and in violet, dementia with Lewy body. You see also, in relation to normal subjects in blue, a clear increase, abnormal increase of delta source activity in occipital areas in all patients group, but especially Parkinson's disease with dementia in green. Then you see again the eyes closed, eyes open conditions and the reduction of alpha rims in the Hans Berger finding. We apply the same paradigm of eyes closed, eyes open to our groups of participants. And so you see in the left in healthy subjects, in blue healthy subjects, the power peak in the sources of alpha in parietal occipital areas in eyes closed, blue, and in the red, eyes open in the left part of the figure. So this reduction of alpha source activity for eyes open condition in the relation to eyes closed condition was very clear in our healthy older persons. In the right side, you see the same picture from Alzheimer's disease with dementia. And you see less source activity in alpha for eyes closed and a little reduction in eyes open condition. So less power of alpha in eyes closed, and low reduction, low reactivity of alpha source in eyes open. And in this picture, you see blue dots are healthy subjects, and the reduction of alpha source activity during eyes open is 0, means the same alpha source activity in eyes closed and eyes open. Lower negative values are related to reduction of alpha for eyes open. So you see any dot is a subject, and most of the participants, healthy, show this reduction of alpha for eyes open. This is not true for Alzheimer's disease with dementia. In the red, you see several persons not showing this reduction of rims for eyes open. And the same was true for patients with Lewy body in green. Several patients do not show this reactivity. And also at the average level, you see that the reduction of alpha source activity for eyes open, which are the negative values, is maximum for blue healthy subjects, almost 70% of reduction, is intermediate in Alzheimer's disease with dementia in red, and it was very poor for dementia with Lewy body. And exactly the same results were observed in a second experiment, including Parkinson's disease with dementia in green. Again, you see that healthy subjects, for the majority of cases, show these negative values, reduction of alpha rims for eyes open. Again, several Alzheimer's disease patients do not show this reduction. And surprisingly, about half of the Parkinson's disease patients do not show this reduction of alpha rims for eyes open. And you see a lot of individuals over the threshold of a percentage reduction of alpha rims for eyes open. And in the right side of the picture, again, you see that a very clear, strong, again, 70% of reduction of alpha for eyes open, in blue for healthy, intermediate for Alzheimer's disease with dementia in red, and very poor for at the group level for Parkinson's disease with dementia. And so this is an experiment showing that these abnormalities in alpha rims may be due to cholinergic system in the brain of Alzheimer's disease. In this experiment, we administered cholinergic therapy to Alzheimer's disease patients with dementia for 1 year, and recorded the resting state eyes closed in baseline before starting the treatment and after 1 year. And here the graph shows the EEG source activity in baseline minus the follow-up after the therapy. And we divided the group in 2 subgroups. The Alzheimer's disease responder to the therapy, showing some stabilization of global cognition in blue, and the group of patients showing a cognitive decline after 1 year, non-responders to the cholinergic therapy in red. In the graph, so negative values show reduction of alpha source activity after 1 year of the therapy. And you see that non-responders from a clinical point of view show a very drop of alpha source activity. The highest negative values of the difference between baseline and follow-up in occipital and temporal alpha source activity. And unfortunately, also the blue group of responders from a clinical point of view show some reduction of alpha rims in occipital and temporal sources. So showing that even if there is some stabilization of cognition after 1 year, the brain show a reduction of alpha rims in the resting state as closed condition. In this slide, you see again the recording of delta rims in the patients immediately after the seizure by Hans Berger. And so we also investigated the epileptiform activity in patients with Alzheimer's disease and mild cognitive impairment without any diagnosis of epilepsy. And here you see 8 Alzheimer's disease mild cognitive impairment subjects showing some peaks and slow waves that were defined as epileptiform-like by our expert of epileptiform activity, our epileptologists. They follow the clinical criteria for the identification of epileptiform activity. And when we compare these patients with Alzheimer's disease and mild cognitive impairment with epileptiform activity, in the figure they are in green, and we compare this with Alzheimer's disease mild cognitive impairment without epileptiform activity in red, there were some group differences. And you see that there is higher abnormal delta source activity in Alzheimer's disease mild cognitive impairment with epileptiform activity, green, in relation to Alzheimer's disease MCI without epileptiform activity in red. So more delta in occipital and temporal sources in the resting state, eyes closed in these patients without a clinical diagnosis of epilepsy. And so one discussion is if you should treat pharmacological these patients with mild anti-epileptic drugs to improve the vigilance, the consciousness level. And briefly, I will introduce the results of a big Latin American Caribbean consortium led by Agustin Ibanez. They collected data from several countries. You see from in blue, not only from Latin American and Caribbean countries, but also some European and Asian countries. In order to put together the data, harmonize the EEG activity in the resting state in these people with healthy aging, healthy brain aging, but also patients with Alzheimer's disease and other diseases. And they correlated EEG, including alpha source activity, with several dimensions, demographic and clinical. And they discovered that EEG source activity in alpha is strictly, as you see, the cortical regions in gray in the maps are related to age, cognition, and sex. And very important, that there is a sort of acceleration of brain aging in females when compared to males globally. And there is a special accelerated brain aging in the females of countries with lower and middle income, so related to less investment in public brain health. And this disadvantage in the brain aging was also observed in Alzheimer's disease patients in Latin American countries. So this raises the issue of the economic factor at the country level on the brain aging of persons, especially females, and the need for social policies counteracting this disadvantage. So we can conclude that in normal brain, there is an alpha dominance in the resting state condition, and in relation to the good cortical connectivity and good subcortical neuromodulatory regulation of cortical arousal and excitability. In Alzheimer's disease brain, this connectivity from the cerebral cortex and the ascending subcortical systems is impaired by the neuropathology. And alpha rims in the resting state as close condition appear to be disrupted or reduced, and with the dominance of slower frequencies. And we propose this, that resting state EEG biomarkers are used as pathophysiological biomarkers of disorders in the regulation of cortical arousal and excitability in quiet vigilance, and the dysfunctions of the vigilance. And they are used together with standard biomarkers of amyloidosis and tauopathy in the brain for the diagnosis. So a neurobiological diagnosis with amyloidosis and tauopathy measures in vivo, and the use of pathophysiological biomarker based on EEG for the assessment of the systems related to an important symptom, the dysfunctions in vigilance and consciousness level. These are my co-workers and the grants supporting my group. So I thank you very much for your attention to this presentation, your patience to follow this celebration of Hans Berger discovery of human EEG and of the World Alzheimer's Disease Day. So I do not see any question in the chat. So I thank you again for connecting to this seminar, and I hope that we will meet soon. Bye-bye.